Hey there, how's it going? It's Mr. Murray coming to you with a video on conditional probability. Okay, so in this video, I'm going to go ahead and break down for you this concept in probability that I started talking about during the Hangout on Wednesday. And what I'll do is I'll go ahead and break down for you what is it and how do we calculate it in a couple different contexts. And then I'll have problems for me to do, us to do, and for you to do. Okay, so to start off, what is conditional probability? So conditional probability is a measure of the likelihood that an event A will happen given that an event B has already happened. So far what we've been doing is we've been calculating probability in a vacuum. We just pretending like, we come along and we pick a card. We come along and we throw a dice. But in life, a lot of things that happen are impacted by events that have happened previously. For example, let's say that I'm a bank and I need to lend money to someone. Now, the reality is, if it's a big amount of money, one where I could potentially make a lot of money, for example, a mortgage, I'm most likely going to have to wait 30 years to get all my money back. So I'm not going to know whether that loan will be successful, right, until 30 years later. So what it would be good is if I could calculate the probability that someone is going to actually pay back their loan. And so basically, the probability will be affected by a number of conditions, right? For example, if the individual has a bad credit history, meaning maybe they paid things late, they maybe got into collections because they hadn't been, they'd owed money to someone, or they've been getting a lot of credit inquiries, right? They've been applying for a lot of credit. If so, that individual, given that they've had that history, they are less likely, or they have a lower probability of paying back the loan, versus someone, on the other hand, with an excellent history of always paying everything on time, right? Having a history of having a lot of different cards, managing credit responsibly, has a higher probability. It doesn't mean that it's going to happen for sure, but the probability that it will or will not happen is based on the previous actions of that person. Similarly, if someone has a steady income, given that they have a steady income, they will have a higher probability of paying it back. Okay, car insurance uses this, right? Given that someone has been in an accident, what is the probability that they will be in another accident? By doing this and using probability, right, car insurance companies can make really accurate models of what they need to charge you so that given certain probabilities, they can ensure they make money, right? Millions, if not billions of dollars are made based on these conditional probability concepts. So what we've got to think about is this. Something's going to happen that's going to affect the situation. And instead of us having to think about every possible scenario, we only have to think of some possible scenarios. Because the one thing a conditional probability does is it reduces the sample space. Because the sample space generally contains every single possible outcome. However, once an event has already happened, some outcomes may not be possible anymore. And so as a result, those will not be in the sample space. And this is something we're going to see in just a moment. I recommend at this point that if some of this is not making sense to you, you consider two things. One, please take a look at the Hangout notes for May 20th, 2020, because in those Hangout notes, I talk about some of the fundamental ideas behind conditional probability, along with some examples. I also recommend you take a look at my video on theoretical probability that I posted earlier this week that I think will be helpful in terms of understanding fundamental ideas behind probability. All right, so without further ado, here we go. So this was actually taken from the Do Now for today. I recommend it. Also, I guess recommend you watch that if you haven't yet done so. So, what is the probability that a person who plays sports for 3 seasons takes 2 honors and AP classes? So, what I've done is I've essentially gone out there and I've done a little survey. Okay, and in the survey, I asked a number of people, one, how many seasons of sports did you play? Okay, when I think seasons of sports, I'm thinking fall, winter, and spring. I'm not really counting summer here. So you could either play 0, you could play one of the 3 seasons, 2, or all of the seasons. Okay, and then how many honors or AP classes do you take? Do you take none, 1, 2, 3, or more? So what is the probability that a person who plays sports for 3 seasons takes 2 honors or AP classes? So the thing here is this. I don't care about everyone anymore, right? I want the probability that a person who plays sports for 3 seasons takes 2 honors and AP classes or AP classes. Okay? So basically what I'm looking at is, first, I need the people who play sports for 3 seasons. And that is this right here. So what you can see is I've reduced my sample space. I no longer want to know about all 100 people. I want to know, out of the people who played sports, out of those 5 people, if I choose one random person, what's the probability they take 2 honors or AP classes? Well, out of these 5 people, 2 of them do that. So there's 3 ways you could report this. Please make sure you're aware of if I ask you to report it in a particular way. For example, please give your answer as a fraction. Please give your answer as a decimal. Please give your answer as a percent. So as a fraction, 2/5. As a decimal, 0.4. As a percent, 40%. Okay? So that's basically the idea. Now, again, notice how it's not out of everyone, but you have to figure out, right, who is it out of, right? It's out of one of these totals you see here. So the strategy and the trick in being successful is which one. And so the good news is, at least I try to make a good effort to talk about this with you guys in 9th grade, but it does come back again, as you guys are seeing. And so if it's something you missed, it's something that we want to make sure we hit on again now. Okay, now here's the next question. So this question was, what is the probability that a person who plays sports for 3 seasons takes 2 honors or AP classes? What is the probability that a person who takes 2 honors or AP classes plays sports for 3 seasons? It's not the same, because the previous one said, if I choose a random person who plays sports for 3 seasons, what's the probability they take 2 honors or AP classes? Here is, if I choose a random person who takes 2 honors or AP classes and 30 people fall into that category, what's the probability they play sports for 3 seasons? Well, out of those 30, only 2 do. So, and I would expect to see that would be reduced to 1 out of 15. So I could have 1 out of 15 as an answer. If I asked for it as a decimal, you probably have to round it to 0.07, because if you do 1 out of 15, you get 0.066666. So you can get 0.07 or about 7%. All right. How about this? What is the probability that a student who does not play sports takes 2 honors or AP classes? The probability that a student who does not play sports takes 2 honors or AP classes. So if I was to pick a random student that doesn't play any sports, what would be the chance they'd be taking 2 honors or AP classes? So who am I going to choose from? Well, who doesn't play sports? Well, that would be 50 people. Half the people responded didn't play sports. Now, of those, we have 15 people taking 2 honors or AP classes. That means that's equivalent to 3 out of 10, 0.3, or 30%, depending on how you're asked to present the problem. All right, so hopefully these have been pretty straightforward. Okay, remember the trick here is figuring out the numerator and the denominator. All right, on this one here, what's the probability that a student who plays sports for 2 seasons takes less than 2 honors or AP classes? So let's take a look. Who are the students who play sports for 2 seasons? Here they are. Sports for 2 seasons. I'm going to try in this one to cross out some of the other rows. So the idea is these rows, we don't care about these rows anymore, right? Because it's based on a condition, right? So given that they play sports for 2 seasons, well, the people who play sports for 0, 1, and 3 seasons don't factor in anymore because they don't meet that condition, the condition of playing 2 sports. So I go ahead and I eliminate those 3 rows, and now all I want to do is focus on this last one. So that means it's easier to see I've got out of 15, and I want less than 2 honors or AP. So that would be 9 and 4 for 13 out of 15, because less than 2 could be 1 or 0. Okay, if you convert that to a decimal, you get about 0.87 or about 87%. So that is to say 87% of the students who play sports for 2 seasons take less than 2 honors and 8. So if I was to choose a one randomly, I'd have almost a 9 in 10 chance that they would be taking less than 2 honors and AP course. Not necessarily, right? There's a 1 in 10 chance they don't, right? But very highly likely they do. All right, so here's one for you to try. So given the exact same table, based on the exact same survey, what is the probability that a student who takes 3 or more honors or AP classes plays sports for 2 or more seasons? So please go ahead, pause the video, find the probability, and then when you're ready, unpause, and you can see what I got. Okay. So what I have is this. A student who takes 3 plus honors. So I need to know, well, who are the students who take 3 plus honors or AP classes? Here they are, right? This is the condition. So I cross out these columns because those students don't meet the condition. Even if it doesn't matter if they also happen to take 0 sports, 1 sports, 2 sports, that doesn't matter because they don't meet the condition of taking 3 or more honors or AP. Only these students do. Okay, so now out of these students, and there are 10 of them, 2 or more seasons would be these 2 right here. So I'd have 2 out of 10, which is equal to 1 out of 5 as a fraction, as a decimal, 0.2, as a percent, 20%. So that is to say, if I was to randomly choose someone who took 3 or more honors classes, there would be a 20% chance that they play sports for 2 or more seasons. Okay, so hopefully this made sense to you and you're able to get it right. If you have any questions at this point, I really recommend you pause and rewind and maybe take a look back at anything I've done previously. And then in a moment, I will move on to the next concept. All right, now I'm going to talk about a little bit of probability involving cards, playing cards to be specific. If you've never seen playing cards, I do want to establish some basics. The first basic That is true, but a deck of playing cards in this case is that the deck will contain 52 cards. 52. The cards are split up into 4 what we call suits. The clubs, the spades, the hearts, the diamonds. There are an equal number of each of them, 13 different ones. So you have 13 times 4 is equal to 52. Right? Now they range from ace. The A stands for ace. Then you have 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right? They represent the numbers on the cards. And then you have 3 what we call face cards. The jack, the queen, and the king, represented by J, Q, and K, respectively. The suit itself, right, the symbol, has no actual meaning in terms of the value of the card. The values you see here underneath, where you see 1 or 11, 2, 3, 4, 5, 6, etc., that is the value of the card if we were playing the game blackjack. Other games might follow that scoring rule as well, but this was originally designed for math around blackjack and probability of winning there. Okay? So basically what I'm going to do, another common type of question, is to ask you probability questions based on these cards. Okay? So here's what I'm going to do. Suppose I was to randomly draw a card from this deck. Okay? And by the way, I will tell you in today's lesson notes, this sample space of cards will appear. Now remember, because we're doing conditional probability, we're not going to end up using the entire sample space, but I'll make this visual available to you so that you have this to look at, so you don't need to memorize any of this stuff about the playing cards, because that's not as well, especially given in some of the online work activities. Okay. So suppose you randomly draw a card from this deck. Event A is that the card is black. I didn't mention that there's 2 suits that are called black suits, and that's because the cards look black. Those are the clubs and the spades. And then there's 2 suits that are called red suits because they are red, and that is the hearts and the diamonds. I think I might have mentioned this. If not, a face card is the card that's a jack, a queen, or a king. Okay, so here are my events. Event A is that the card is black. Event B is that the card is a spade. Event C is that the card is a jack. And event D is that the card is not a face card. So, keep in mind, I'm going to stay with these 4 events and we'll be solving problems using these. You'll see similar problems most likely show up in the My HRW work. All right, so remember this notation, B bar A, the bar means given that, and then A is the thing that has already happened. So this means the probability. So what I'm going to do is this. Someone's going to shuffle, shuffle, shuffle. I'm going to randomly draw a card. For all of these activities, I want to clarify, you should assume that once you've drawn that card, you return it to the deck so that there are always 52 cards in the deck. This is called with replacements. Okay, so there's 2 types of problems, with replacement and without replacement. With replacement means I put it back. And that's important because if I was to draw another card, that would affect the probability. Because now if I draw the next card, if I didn't replace the first one, there are now only 51 cards to choose from. So we're going to assume there are always 52 cards to choose from. Now, will all of them be relevant based on the condition? No, but I'm just saying the previous answers don't have any impact on the subsequent ones, okay? So the probability that the card is a spade that I draw randomly, given that the card is black. So if the card is black, that means that hearts and the diamonds are not black cards, they're red cards. So what that means is that I'm no longer going to consider them because they're not in the sample space anymore. So given that the card is black, that means that there's 26 cards that meet that description. And how many of them are spades? 13 of them are. Right? I've got my 13 spades out of my total 26 black cards. So that's 1/2, 0.5, or 50%. Again, depending on how you're asked to give the answer. Okay, now for the next part. What is the probability that the card is not a face card given that the card is a spade? So where are the spades? Here they are. So these are the only, right? Because if you think about it, if the card is not a spade, then it doesn't really matter, right? So because the whole idea is this: the fact that a card is a spade is again reducing our sample space, right? We know the card's a spade, so we know we're not concerned about what happens with the clubs. We're not concerned about what happens with the hearts. We're not concerned about what happens with the diamonds. So given the card's a spade, we're out of 13. The probability it's not a face card, well, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cards that are not face cards. So that's 10 out of 13. Here's the other way to look at it. There are 3 cards that are face cards. So 13 minus 3, or 10, are not, right? If 3 are, then 10 are not, right? So you could look at this as if you had an event E, card is a face card, then you could look at E as being equal to the complement of D, right? The opposite in a sense. Okay. So we could look at 10 out of 13. If we were to try to evaluate that, we would get 0.769 or 76.9%. Okay, again, depending on how you're asked, and again, depending on how many decimal places you're asked to provide. Okay, so hopefully this made sense. If not, please go back and rewind and take a look at anything I've done. And then in a moment, I will move on to the next couple of examples. Okay, so now, suppose you randomly draw a card from this deck. So A is the card, so we've got the same deck, right? 52 cards, etc. Event A, again, the card is black. Event B, the card is a spade. Event C, the card is a jack. And event D, the card is not a face card. The events themselves have not changed. What's the probability that the card we randomly choose is a jack given that it is black? So again, because given that it is black, that's 26 total cards, right? Just like when we saw in this last one. When we saw, given that it's black, we identified that. Given that it's black, it's out of 26 because there's 26 black cards. If we choose a card randomly, there are 2 possible jacks we could pick from. So it would be 1 out of 13 because it's 2 out of 26. Please always reduce any fractions. Okay? Please make them as reduced as possible. Please and thank you. So 0.076 or 7.6%. Again, depending on how you're asked to deliver it. On the other hand, what's the probability that a card is black given that it is a jack? It's an interesting question. Given that it is a jack, well, how many jacks are there? 1, 2, 3, 4. There are 4 jacks. How many of them are black? 2. So that's 1/2, 0.5, or 50%. So this was the word trick that I kind of tried to get at when we were working in the two-way table, where we talked about one, then we flip around the words with the AP class and the sports. So this says, what's the probability that a card is a jack given that it's black? So given that a card's black, you have a 2 in 26 or a 1 in 13 chance of getting a jack because there are 2 jacks out of 26 black cards. But when I tell you, given that a card is a jack, that's a little bit different, right? Because now, given that's true, there's only 4 cards that it could possibly be, right? If I tell you, okay, you're going to draw a jack, if you know you're already going to draw one, well, then you know of the 4 jacks I could draw, 2 of them are black. So therefore, I have 2 out of 4 or a 1 in 2 chance of drawing a black card, given that I know it's going to be a jack. Okay, probability is not easy stuff, but if you try to look at it from a conceptual way and really think through it and be a problem solver, you can really, really be successful with this stuff at a high level. All right, now another one for you to try. So I've got these two. The deck is the same. Again, you're not keeping the cards out. You're always putting them right back in there. Okay, so that there's no effects from any of the previous questions. You're starting with a full 52 card deck, and we're randomly drawing a card from the deck and then putting it back in. These are the exact same 4 events they've always been. So what I want is the probability that a card is a jack, given that it's a spade, and the probability that a card is a spade, given that it is not a face card. So please pause the video, find these 2 probabilities, then when you're ready, unpause, and you can see what I got. All right, let's take a look. So, probability that a card is a jack given that it is a spade. So there are 13 spades, of which one of them is a jack. Okay, so I'm just going to do these as percents, or rather as fractions. I think we've seen from the last one 0.076 if you wanted to really write it as a decimal. What is the probability that a card is a spade given that it's not a face card? So these are the cards that are not face cards. Now, these are a lot to count. So what I'm going to do is I'm going to take a look at it in a different light. So we know there's 52 cards in the deck. We know that 3, 6, 9, 12 of them are face cards. So if there's 52 cards and there's 12 we don't want, then there's 40 we do want. So it's out of 40. And now what I want to know is, out of those, which of them are spades? And that, you got to be careful, is 10, because you don't include the face cards. You only include the spades that are also face cards. So you've got to be really, really careful there. It's the same idea as when you're doing the two-way frequency table. It's very, very similar. You want to look at the overlap, where the 2 things overlap out of the total at the bottom of the column or the end of the row. Okay, so that's a 1, 4. All right, so you got a 25% chance. And if you think about it, this kind of makes sense. Spade, given that it's not a face card. So if you think about it, of all the cards that are not face cards, the spades make up a quarter of them, right? Because they're a quarter of the overall cards. So everyone has the same number of face cards. So they would be the total number. They'd make up the same percent, rather, of the not face cards. Okay, last example. So we're going to use the percentages in this table, or the values, to find the probabilities that we've been requested. And we need to write our answer as a percentage rounded to an integer, which means to a whole number. The table shows the results of a poll of randomly selected high school students. They were asked if they think smartphones should be allowed in class. What is the probability that a 9th or 10th grader answered yes? So here, 9th or 10th grader, how many of the people are 9th or 10th graders? That would be 0.54. Of those 9th or 10th graders, how many of them answered yes? 0.31. So we do 0.31 out of 0.54. We get if we need to round, we get about 57%. Okay, what is the probability that 11th or 12th grader answered no? So given that 54, that's right. Given that 54% of the people are 9th or 10th graders, I almost got thrown off there. Never mind. So given that 54% of them are 9th or 10th graders, 46% of them are 11th or 12th graders. Okay? And now of those, right, these 9.09 said no. So I go to my calculator, I do 0.09 over 0.46, and I get approximately 20%. You get 19.5, and that rounds up to 20. All right, last two, what I want to do is I'm going to ask you to pause and please calculate. So again, take a look at our table. I want you to pause the video, calculate the answers to question 3 or 4 as a percent rounded to the nearest whole number. Then when you're ready, unpause, and you can see what I got. Okay, so probability that a 9th or 10th grader, 9th or 11th grader rather, answered yes. So 9th or 11th graders, how many of those are there? So if I'm in 9th or 11th, that's 27 plus 24. So out of 0.51, and answered yes, 19, and that would be 0.34. So I have 0.34 out of 0.51, and I get approximately 67%. Believe it or not, I got 66 per 2/3, basically 666.6666, and that's because it's 2/3. What's the probability that a 10th or 12th grader answered no? So between 10th and 12th, I have 0.49 when you add up those. Answered no, 0.11 and 0.04 for a total of 0.15. Okay, so I put that in my calculator, and I get approximately 31%. So folks, hopefully you found this video to be helpful. I will have a follow-up assignment on HRW where I'll need you to answer about at least 8 out of 10 questions about probability, but the problems are just like this, okay? We're taking a look at a sample space. We're looking at an event that's already happened that has changed things in some sense. We're analyzing the impact of that change, and then we're using it to calculate the probability that that something has happened, given that that other event has already happened. All right, please stay tuned for all my updates that I'll have coming on probability. Please make sure you're staying up to date with work, as we'll move on pretty quickly with probability. I'll have some other stuff coming in the future. But best of luck, folks. Don't forget to love math. And remember, you can do it. Until next time, don't forget to like and subscribe, and have a wonderful day.